It began not with a roar, but with a shudder, a deep, resonant hum that vibrated upwards through 700 kilometers of solid rock, a dissonant chord struck on a geological piano the size of a continent. On the surface, the Pacific Ocean barely registered the disturbance, its waves continuing their timeless rhythm, oblivious to the violence stirring in the planet's forbidden depths. But in laboratories across the globe, 1,000 silent sentinels screamed. Seismographs, the delicate nerves of our world, leaped from their slumber. Needles thrashed against paper, and digital displays flooded with crimson alerts tracing the signature of an impossible event. This was not the familiar shallow fracturing of tectonic plates grinding past one another, the geological friction that remodels our coastlines and topples our cities. This was something else entirely, something ancient and profound. The signal originated from a place where earthquakes are not supposed to happen, a region of the lower mantle where the pressure is over 24 gigapascals and the temperature is so extreme that rock should flow like thick honey. In this realm of crushing forces, brittle fracture, the sudden snap of rock that generates seismic waves is a physical heresy. Yet the data was undeniable. Something down there in the dark, hot heart of the world had broken. It was the deepest, most powerful deep focus earthquake ever recorded, a ghost in the planetary machine. For the geophysicists who first saw the readings, it was a moment of profound confusion and awe, a message from a world beneath our own that we have barely begun to comprehend. They called it the Tonga anomaly, a tremor that defied the known laws of rock mechanics, a geological paradox that shook our most fundamental assumptions about the planet we call home. What force could possibly cause solid rock to shatter under such hellish conditions? What unimaginable stress could be brought to bear so far from the familiar tectonics of the surface? The Earth, it seemed, was keeping a violent secret. The investigation began immediately, a global effort to model the unmodelable, to understand the physics of a place we will never visit. But the answer to this profound terrestrial mystery, the key to unlocking the secret of the Tonga anomaly, would not be found by digging deeper into our own world. It would be found by looking up out into the limitless silent expanse of interplanetary space. The answer impossibly was already on its way. At the very same moment our planet was ringing like a bell from this internal blow, a silent traveller was slicing through the ecliptic plane of our solar system. It was a phantom, a whisper from the void, christened 3I, Atlas. The I, in its designation, is what set it apart, a simple letter that carried with it the weight of cosmic loneliness and immense discovery. It stood for Interstellar. This object was not one of ours. It was not born from the same protoplanetary disk as Earth, Mars, or Jupiter. It was not a prodigal child of our sun returning from the cold outer darkness of the Oort cloud. It was an alien, a refugee from another star system, a celestial messenger carrying within its frozen heart the chemical secrets of a sun and planets you will never see. Its journey was one of unimaginable scale. For millions, perhaps hundreds of millions of years, it had wandered the star-strewn desert between worlds, a dark, inert rock of ice and dust, tumbling alone in the absolute zero of the interstellar medium. The starlight it reflected was not from our sun, but from alien constellations distant and strange. It had outlived its own parent star's main sequence, or perhaps it was violently ejected from a nascent planetary system in its chaotic formative years. We will never know its true origin story. What we do know is that by a 1 in a trillion chance, its lonely, silent trajectory brought it into the gravitational grasp of our solar system. Pulled from its ageless interstellar cruise, it began to accelerate, falling toward a star it had never known. For the astronomers at the Asteroid Terrestrial Impact Last Alert System in Hawaii, it first appeared as nothing more than a faint fuzzy smudge on a digital sensor, another faint comet perhaps on a long looping orbit. But as they tracked its path night after night, a startling picture emerged. This was no gentle elliptical orbit. This was a hyperbola, the unmistakable arc of an object moving so fast it was destined to escape the sun's gravity and return to the interstellar darkness from whence it came. It was a one-time visitor, a fleeting guest in our cosmic home. As it plunged closer to the sun, the alien ice, untouched for eons, began to feel the warmth. Gases that had been frozen solid since the dawn of time began to sublimate, erupting from its surface and shrouding the nucleus in a glowing coma of vaporized history. A tail, a diaphanous banner of dust and ionized gas, began to unfurl behind it, pointing away from the sun like a cosmic windsock. It was a celestial blowtorch aimed at a primordial snowball, releasing the preserved atmosphere of a world that died before humanity was born. This was only the third such interstellar visitor ever confirmed, a rare and priceless opportunity to study matter from beyond our celestial backyard. Yet 3I, Atlas, held a significance that went far beyond its chemical composition. Its arrival, its precise path through our system, was about to become the central clue in a geological investigation that would span two seemingly disconnected realms of science. Here, then, is where our story truly begins, at the intersection of two impossibilities. On one hand, a planet breaking its own rules, shattering in a place where it should be fluid. On the other, a visitor from another star briefly gracing our solar system with its presence. Two distinct, monumental events occurring in the same narrow window of time. Separated by over 100 million kilometers of empty space, what possible connection could there be? In the halls of academia and science, the very suggestion is a form of heresy. The disciplines are separate. The geophysicist studies the Earth's mantle. The astronomer studies the stars. One looks down, the other looks up. The forces that govern the deep Earth are immense, ponderous and internal. The residual heat of planetary formation, the slow, inexorable churn of convection currents moving continents. The forces exerted by a passing comet, a mere 10-kilometer wide ball of ice and rock, are by comparison cosmically insignificant. Its gravitational pull on the Earth is less than that of a commercial airliner flying overhead. To suggest that this celestial flyby could influence the deep mantle is like claiming a butterfly's wing beat could trigger a volcanic eruption on the far side of the world. It seems to violate every principle of scale and force that we hold dear. It is on its face absurd. And yet, the coincidence is too perfect to ignore, the timing too precise to be mere chance. As 3I, Atlas, reached a specific point in its hyperbolic arc, a point of subtle gravitational resonance with our planet, the Tonga anomaly occurred. The deepest earthquake ever known was born. Could there be a thread connecting these two events, an invisible filament of force stretching across the vacuum of space, reaching down through our atmosphere, our oceans, our crust, and deep into the molten heart of our world? Could a whisper from an interstellar wanderer be amplified into a tectonic scream? This is the question that lies at the heart of our investigation, a question so profound, so challenging to the orthodoxy of science that most would dismiss it out of hand. But a new generation of scientists armed with unprecedented data and a willingness to explore the fringes of possibility are daring to ask it. They are proposing mechanisms that sound like science fiction, not a simple gravitational tug, but something far more subtle and exotic. Could the comet's passage have disturbed the dark matter halo that surrounds our planet, causing a fleeting, localized density shift that stressed the mantle below? Could it have emitted a focused jet of high-energy particles, a byproduct of its interaction with the sun's magnetic field, that penetrated deep into the Earth, altering the physical state of the rock in that forbidden zone? Or could it be a phenomenon we don't even have a name for yet? A new physics of cosmic interaction that only reveals itself during these rare interstellar encounters. The search for this connection forces us to reconsider the very nature of our planet. We have always thought of Earth as a fortress, an isolated bastion of life protected by its magnetic field and thick atmosphere, a self-contained system governed by its own internal rules. But what if it isn't? What if our planet is more sensitive, more intimately connected to the wider cosmos than we ever dared to believe? What if the void is not so empty after all, but is instead crisscrossed by invisible lines of force, by streams of exotic matter, by influences that can reach out and touch us in the most profound and violent ways? The implications are staggering. It would mean that the history of our world, the very rhythm of its geological heartbeat, might be punctuated by the passage of these silent visitors from other stars. It would mean that the greatest threats and the most powerful influences on our planetary stability might not come from within, but from without. To find the truth, we must embark on a journey that will take us from the deepest layers of the Earth to the farthest reaches of the solar system. We will join the seismologists as they dissect the strange signature of the Tonga anomaly, searching for clues in the waveforms that point to an external trigger. We will stand with the astronomers as they analyze the light from 3i, Atlas hunting for any sign of unusual emissions or behavior as it passed our world. And we will enter the esoteric world of the theoretical physicists who are trying to build a bridge of mathematics and new ideas to connect these two impossible events. What we are searching for is more than just the solution to a geological puzzle. We are searching for a new understanding of our place in the universe. Are we living on a lonely, isolated island in a vast, empty ocean? Or are we and our world part of a dynamic, interconnected, and potentially dangerous cosmic web? The answer may force us to look at the sky not with just wonder, but with a newfound sense of awe and perhaps a touch of fear. The evidence is waiting. We just have to be brave enough to follow where it leads. Is it possible for the ground beneath your feet, this symbol of all that is solid and dependable, to be fundamentally hollow, not in structure but in certainty? We live our lives on a planetary shell, a brittle eggshell of cooled rock floating on an ocean of molten fire. And we believe we understand its rules, the groaning mechanics of its tectonic machinery. We've learned that when this crust fractures, it releases the energy we call an earthquake. A violent but comfortingly familiar process born of plates grinding against each other in the planet's accessible upper layers. This is the story we tell ourselves. A story of surface tension. A story that we are now beginning to realize is profoundly incomplete. Because a world away from the sunlit surface, in the crushing eternal darkness of the deep earth, something is happening that should not be possible. Something is breaking the rules. Our planet's interior is a place of truly unimaginable extremes. Journey with us just a few hundred kilometers beneath the soil and the sea. Here, the sheer weight of the world above creates pressures that can crush diamond and temperatures that can melt iron. In this realm, rock itself ceases to be rock as you or I would know it. It doesn't shatter, it flows. Under this titanic strain, the mantle behaves like a colossal river of ultra-viscous tar, a plastic, ductile medium churning in convection cycles that span millennia. Brittle fracture. The very thing that causes an earthquake is a physical impossibility, or it should be. Yet our most sensitive instruments, our planetary stethoscopes, have for decades been picking up a ghostly shiver from this forbidden zone, a heartbeat from a place that should be silent. These are the deep focus earthquakes, the terrifying phantoms of seismology. They are not born of grinding plates at the surface, but are triggered in the abyssal depths from 300 to more than 700 kilometers down. They are anomalies that defy our most fundamental understanding of geology, violent ruptures occurring where nothing ought to be capable of rupturing at all. To even begin to understand these enigmas, we must look to the planet's great recycling system, the subduction zones. These are the colossal trenches where the ocean floor, a gargantuan slab of cold, dense lithosphere, ends its long journey across the globe and begins to die. In an inexorable, grinding descent that takes millions of years, this oceanic plate is forced to dive beneath a lighter continental plate, plunging back into the searing heat of the mantle from which it was once born. It is a process of planetary cannibalism on a scale that dwarfs human comprehension. This descending slab becomes a geological ghost, an immense frozen dagger of brittle rock being thrust into the planet's pliable heart. For a time, it retains its rigidity, its memory of being cold and solid, even as it is surrounded by a hellish furnace. It is this skeletal slab, and this slab alone, that carries the potential for brittleness into the forbidden depths. It is a conduit for a type of violence the mantle should have long forgotten. But even with this cold slab, the mystery only deepens. As the plate descends, the pressures and temperatures eventually become so overwhelming that even its resilient minerals should surrender, transforming into more ductile forms. So what could possibly trigger a sudden catastrophic fracture hundreds of kilometers down? Scientists have chased this phantom for generations, proposing theories that sit on the very edge of our knowledge. One leading hypothesis speaks of dehydration, embrittlement. The minerals within the sinking slab are hydrated, meaning they have water locked directly into their crystalline structures. As the slab is squeezed by the mantle's grip, this water is violently expelled, This superheated high-pressure fluid could in theory fracture the surrounding rock from within, like a hydraulic hammer of unimaginable power, creating a fault where none should exist. It is a compelling, elegant idea, painting a picture of the planet's own water turning against it in the deep. Yet there is another, more exotic suspect, one that speaks to the very alchemy of matter under pressure. It is a theory of transformational faulting. The primary mineral in the upper mantle is olivine, a common olive-green silicate. But as the subducting slab carries this olivine down past a depth of about 410 kilometers, it crosses a thermodynamic boundary, a point of no return. The crushing pressure forces the olivine's atoms to violently reconfigure themselves into a far denser, more compact crystal structure, a mineral known as spinel. This is not a gradual change. It is a sudden, explosive phase transition. The theory suggests that within the coldest, deepest core of the slab, pockets of olivine might persist far below their stability zone, becoming a kind of geological explosive. When they finally do transform, the change is so rapid and so violent that the crystals shear past each other, creating a spontaneous, self-organizing fault plane in an instant. An earthquake born not from stress, but from the very atoms of the rock changing their identity. For decades, we have listened to these deep, unsettling tremors, each one a clue from a world we can never visit. We map their epicenters, chart their depths, and debate their origins. They are rare, accounting for only a tiny fraction of the planet's total seismic energy. But they are also disproportionately powerful, releasing their fury with terrifying efficiency. They remind us that the solid ground is an illusion and that a deep, dark and violent engine is operating far beneath our notice. And on the 28th of May 2023, that engine produced a masterpiece. In the earth beneath the Bonin Islands south of Japan, seismometers across the globe registered a convulsion of profound significance. The initial readings were almost unbelievable, pointing to an event so deep it stretched the very limits of our models. The data, when it was finally confirmed, was staggering. A magnitude 7.2 earthquake originating at a depth of 751 kilometers, deeper than any reliably recorded earthquake in human history. It was a tremor from the boundary of the lower mantle, a place so alien and extreme it might as well be the surface of another planet. This was the geological shot heard round the world. A singular event that sent geophysicists scrambling, an impossible rupture that demanded an extraordinary explanation. The Earth, it seemed, had revealed a new, more profound layer of its mystery. But as seismologists stared down into the abyss, they were completely unaware that the clue to this unprecedented event might not lie in the Earth's core at all. It might have come from the cold, silent vacuum of interstellar space. The universe is in constant motion, a swirling, chaotic dance of gravity and light. Our solar system, which feels so vast and permanent to us, is in truth just a tiny, isolated island in the immense ocean of the Milky Way galaxy. The comets and asteroids we see, the familiar wanderers of our celestial neighborhood, are overwhelmingly local. They were born here with our sun from the same primordial cloud of gas and dust. They are part of our family, orbiting in predictable closed loops, held fast by the sun's gravitational leash. They travel out to the frozen frontiers of the Kuiper Belt or the ghostly Oort cloud, but they always come back. They are ours. But every so often a traveller from a distant shore washes up on our island, an object with a past we cannot know, a history written in the light of another star. These are the interstellar objects, cosmic phantoms ejected from their own solar systems and sent careening through the void for eons. They are messengers carrying physical evidence from alien worlds, and their arrival is an astronomical event of the highest order. For most of history, their existence was purely theoretical. Then, in 2017, we met the first Oumuamua, and just 2 years later, a second appeared, a more traditional yet no less extraordinary visitor. On the final days of 2019, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey in Hawaii, flagged a faint smudge of light moving against the background stars. At first, it was catalogued as just another Comet C, 2019 Y4, but as astronomers tracked its path, they saw something that made their hearts pound. Its trajectory was not a gentle closed ellipse like the comets of our own system. It was a wide-open, screaming hyperbola. This object was not turning around. It was not bound by our sun's gravity. It was a cosmic bullet fired from an unknown cannon in the interstellar deep, and it was just passing through. The designation was updated. It became 3I Atlas, only the third confirmed interstellar object ever detected. It was a ghost from the space between the stars, and it was heading our way. Its journey had been one of unimaginable loneliness and scale. We can only speculate about its origins. Perhaps billions of years ago it formed in the swirling protoplanetary disk of a young sun-like star hundreds of light years from here. Perhaps it witnessed the birth of giant planets, great gas orbs whose gravitational meddling eventually turned its stable orbit into a chaotic escape route. It was a piece of gravitational shrapnel flung from its home by a planetary slingshot. For millions, perhaps hundreds of millions of years, it drifted through the absolute zero of the interstellar medium, a silent, frozen relic traveling in darkness, tumbling end over end its surface, accumulating the dust and radiation of the galactic wilderness. It passed through nebulae, skirted the edges of other star systems, and witnessed cosmic histories we can only dream of, all while carrying the chemical fingerprint of its long-lost birthplace. Then by sheer dumb luck, its eons-long trajectory intersected with our tiny corner of the galaxy. It fell into our sun's gravity well, not as a captive, but as a temporary guest on an unstoppable journey. As it plunged inward, the distant, warming light of our sun began to work on its ancient, frozen body. The ices that had been dormant for geological time began to sublimate, erupting from its surface as jets of gas and dust. This outgassing created a faint but visible coma, a temporary atmosphere that gave it the classic cometary appearance. But this process was also a clue. The specific way it brightened and the subtle non-gravitational forces pushing on it told us something about its composition. It was rich in volatile ices, but also possessed a nucleus that seemed fragile, perhaps even fractured from its violent past. Unlike the inert, rocky Oumuamua 3I, Atlas was a dynamic living piece of another world, actively shedding its skin as it raced through our home. Its path was meticulously calculated. It would swing around the sun inside the orbit of Mercury before being flung back out into the void, never to return. Its passage was a fleeting scientific opportunity, a chance to study a piece of pristine alien matter up close. Its closest approach to Earth's orbital path was plotted with pinpoint accuracy. A moment when this visitor from another star would cross our planet's celestial highway. And here the two threads of our story, one born in the hellish pressure of the deep Earth and the other in the frozen emptiness of deep space, begin to converge in a way that is almost too perfect to be believed. The impossible earthquake, the deepest seismic event ever recorded at 751 kilometers, occurred on May 28, 2023. A singular anomalous convulsion from the very base of the upper mantle. The interstellar comet 3I, Atlas, made its closest, most intimate passage across the orbital plane of Earth just 72 hours later. Two utterly disconnected phenomena. One a matter of violent subterranean mechanics, the other a case of silent celestial geometry. They should have no relationship whatsoever. The forces of geology are driven by the internal heat and mass of our own planet. The paths of comets are governed by the gravity of the sun and the laws of orbital mechanics. The two disciplines do not speak to each other. They operate in different worlds on different scales, driven by different physics. The notion that one could influence the other is by any conventional scientific standard absurd. It is the stuff of fantasy, not physics. And yet the timing hangs there in the data, shimmering with unnerving precision. A coincidence so profound it feels like a whisper. 72 hours. Out of the billions of years of Earth's history and the millions of years of the comet's journey, these two unique record-breaking events unfolded in the same 3-day window. It is a statistical ghost, a temporal alignment so unlikely that it forces us to ask a question that most scientists would rightly dismiss out of hand. Could it be possible? Is there some unknown, undiscovered physical mechanism, some exotic form of interaction that we have never conceived of that could link a passing interstellar phantom to the innermost shudders of our world? Could the flyby of 3I, Atlas, have been the trigger, the cosmic, a feather that tipped the scales in the planet's deepest, most volatile regions, causing a rupture that would otherwise not have happened. We stand at a precipice of understanding, faced with an event that challenges the very foundation of planetary science. Before we can even begin to hunt for a mechanism, we must first entertain the possibility of the crime itself. A coincidence of impossible scale, or the first hint of a new and terrifying connection between our world and the greater cosmos. And so, while our gaze was fixed upward, captivated by the spectacle of a visitor from the outer dark, the earth beneath our feet was writing a different story. It began not with a violent lurch or a city-shaking roar, but with a nearly imperceptible tremor, a ghostly signal emerging from the planet's deepest interior. This was a message from a place we can never visit, a realm of crushing pressure and unimaginable heat, where the very rock of our world flows like pitch over millennia. The signal travelled for long, silent minutes, racing up through the mantle, a faint cry from the abyss. By the time it reached the surface, it was a whisper, a delicate filigree of data traced by a network of the world's most sensitive seismometers. In a quiet data processing center in Pasadena, an automated system flagged it instantly. The event's location was beneath the Tonga-Kermadec Trench in the South Pacific, a notorious subduction zone where the Pacific Plate dives violently under the Australian Plate. But it was the depth that caused the software to blink in disbelief. 751 kilometers, nearly 470 miles straight down. This was the lower mantle, a region so compressed that conventional earthquakes born of brittle snapping rock were thought to be impossible. A quake this deep was a geological phantom, a contradiction in terms. It was less a fracture and more a sudden, violent transformation of matter itself, a catastrophic collapse of mineral structure under a strain that defies comprehension. It was by a significant margin the deepest seismic event ever recorded, a monster lurking in the planetary basement. For the seismological community, it was a stunning discovery, a puzzle that would rewrite textbooks on planetary dynamics. It was a purely terrestrial event, a family matter for geologists to debate and dissect for years to come. The conversation was about phase transitions, thermal shear instabilities, and the esoteric physics of olivine under duress. The cosmos, it was universally agreed, had nothing to do with it. The Earth's engine operates on its own schedule, driven by the colossal slow-motion churning of its interior, utterly indifferent to the fleeting celestial light show playing out in the heavens above. The timing, everyone understood, was just that, a coincidence, a remarkable, head-scratching but ultimately meaningless coincidence. But was it? In a small, cluttered home office in rural Oregon, thousands of miles from the hushed halls of academic geology, Leo Jansen was looking at two screens. On his left, the live feed from the Incorporated Research Institutions for Seismology, displaying the newly christened Tonga event in all its perplexing glory. On his right, an orbital mechanics simulator he had built himself tracking the precise position of Comet 3I, Atlas. Jansen was not a professional scientist. He was a retired software engineer with a lifelong obsessive passion for the patterns of the universe, from the intricate dance of tectonic plates to the grand sweeping waltz of comets and planets. He saw the world as a single interconnected system, a place where subtle harmonies and hidden resonances were waiting to be found. For weeks he had followed the comet's journey, marveling at its fragmentation, its ghostly green coma, its silent passage through the inner solar system. And now he was watching the Earth's own deep, resonant response. He toggled between the windows, his fingers tapping on the keyboard. He brought up the comet's trajectory, a graceful arc, swinging it past the sun and then hurling it back out toward interstellar space. He plotted its point of closest approach to Earth, its perigee. Then he overlaid the timestamp of the Tonga earthquake. The two events, the moment of maximum depth for the quake and the moment of minimum distance for the comet, did not just align, they were nearly synchronous, a shiver, an intake of breath. He checked the data again, running the numbers, convinced he had made an error, but the correlation remained stark and undeniable on his screen. A celestial visitor from the dawn of time grazes our planet, and at that very moment, the Earth's mantle experiences a convulsion of unprecedented depth and power. Coincidence, perhaps, but in Jansen's world of intricate code and universal patterns, a coincidence of this magnitude felt like a bug in the software of reality. It felt wrong. It felt like a clue, With trembling hands, he drafted an email. He sent it not to a general inquiry address, but directly to a geophysicist whose work he had long admired, Dr. Aris Thorne at the California Institute of Technology. The message was brief, respectful, and contained just two simple charts laid side by side. One showed the comet's proximity to Earth over a 48-hour period. The other showed the seismic energy release from the Tonga Trench over the same window. The two peaks, one from space, one from the deep Earth, were almost perfectly superimposed. Janssen ended the email with a single humble question: could there be a connection? He hit send and leaned back, his heart pounding. He knew how it would sound. It was the kind of speculative leap that careers were built on avoiding. It was fringe thinking. It was, to be blunt, scientific heresy. The initial reaction within Thorne's small, close-knit research group was precisely that polite, dismissive amusement. The email was flagged as interesting correspondence and filed away. The core of the problem, the reason the idea was so outlandish, came down to a single insurmountable force: gravity. The laws of celestial mechanics honed over centuries are unforgiving. Gravity is a force of mass in a comet, even a spectacular one like 3I. Atlas is a cosmic featherweight. It is a loose agglomeration of ice, dust, and rock, a dirty snowball perhaps a few kilometers across. Its mass is measured in trillions of kilograms, a number that sounds impressive until you place it next to the Earth, a dense ball of iron and silicate weighing in at 6 septillion kilograms. The gravitational influence of the comet on our planet was, to put it mildly, infinitesimal. Thorne's team ran the calculations as a thought experiment, a way to definitively put the amateurs' strange idea to rest. They modelled the tidal forces exerted by the comet at its closest approach. We are all familiar with the tides, the daily breath of the ocean drawn in and out by the gravitational pull of the moon and, to a lesser extent, the Sunday. This same force gently kneads our planet's solid crust, causing it to bulge and stretch by several centimeters each day. It's a powerful planet-shaping phenomenon. The tidal force from Comet 3I, Atlas, however, was a completely different story. The numbers that came back from the simulation were laughably small. The pull it exerted on the Earth's crust was less than the gravitational tug of a commercial airliner flying at 3,000 feet. The stress it induced on the Tonga Trench was a whisper, a phantom touch millions of times weaker than the tectonic stresses already accumulating there every single second. To suggest that this impossibly faint nudge could trigger a cataclysm 751 kilometers deep was like suggesting a butterfly's wing beat could shatter a bank vault. The hypothesis wasn't just improbable, it was physically absurd. Gravity, the most obvious and powerful cosmic force, was a dead end. The case appeared to be closed. But the image of those two perfectly aligned peaks haunted Aris Thorne. It was too clean, too elegant to be mere chance. Science is built on skepticism, but true discovery often begins when we grant a moment's credence to the impossible. What if they were looking in the wrong place? What if gravity wasn't the messenger? The team gathered around a whiteboard, the official work of the day forgotten, drawn into the sheer audacity of the puzzle. If the comet didn't pull the trigger, could it have somehow pushed it? The conversation drifted from the solid Earth to the fluid gaseous envelope surrounding it, the atmosphere. A comet is not just a solid body, it is a dynamic, leaky object. As it neared the Sun 3I, Atlas was a celestial blowtorch sublimating its ices and shedding a vast, tenuous cloud of gas and microscopic dust in its wake. Earth in its orbit didn't just fly past the comet, it flew through the outermost tendrils of this cometary ghost. This led them to a far more exotic and intriguing possibility. What if the interaction happened not in the realm of gravity, but in the realm of atmospheric dynamics? As Earth ploughed through this thin veil of cometary debris at over 100,000 kilometers per hour, the encounter would have been incredibly energetic. The tiny particles, each no bigger than a grain of sand, would have vaporized high in the mesosphere, creating a spectacular meteor shower for any keen-eyed observer. But they would have done more than that. This sudden injection of mass and energy, spread out over a vast area of the upper atmosphere, could have created a pressure wave. Not a sound wave you could hear, but a vast, silent, continent-sized ripple of air pressure an atmospheric tide propagating downward from the edge of space. They called it an acoustic gravity wave, a slow-moving disturbance that could in theory travel all the way to the ground. Once it reached the surface, this wave would manifest as a tiny, fleeting change in barometric pressure. Imperceptible to us, it would be a vast distributed load pressing down on the surface of the Pacific Ocean. The numbers were still small, a pressure change of just a few pascals equivalent to adding a few sheets of paper on top of every square meter of the sea. It seems once again like an impossibly delicate touch, but here the geology of the Tonga Trench provided a crucial piece of the puzzle. Subduction zones are systems in a state of exquisite violent tension. The descending Pacific plate does not slide smoothly into the mantle. It snags, it sticks, it bends, accumulating stress over centuries like a drawn bowstring. The rock at 751 kilometers deep on the verge of a catastrophic phase transition was likely in a state of what physicists call criticality. It was primed, it was balanced on a knife's edge, holding back unimaginable energy, waiting for the smallest, most insignificant perturbation to push it over the edge. Suddenly, the hypothesis didn't seem so absurd. The atmospheric pressure wave wasn't the cause of the earthquake. It was merely the final synchronized trigger. It was the feather that landed on the scale at the exact right moment. The comet didn't need to be a sledgehammer. It only needed to be a whisper, arriving at the precise instant that the deep Earth was ready to scream. The team was electrified. This was a mechanism, speculative yes, but physically plausible. It was a chain of causality, however tenuous, that connected the dust of a dying comet to the deepest heart of our planet. It explained the uncanny timing, the one in a billion coincidence that had troubled Janssen and Thorne. The idea moved from the wastebasket to the whiteboard, and from the whiteboard into the realm of serious, if still clandestine, investigation. Yet another possibility, even more bizarre, began to surface in their late-night brainstorming sessions. This one focused on the nature of the cometary dust itself. These were not just inert specks of rock and ice. They were particles that had travelled for millions of years through interplanetary space, bathed in the constant flow of the solar wind. They would be electrically charged, carrying a small but significant electrostatic potential. What would happen when a shower of these charged particles, a literal cosmic current, slammed into the Earth's magnetosphere? The planet's magnetic field, our shield against solar radiation, is a dynamic and complex system. A sudden, unexpected influx of charged particles could, in principle, create a powerful electromagnetic pulse. This pulse would induce telluric currents, rivers of electrical energy flowing through the planet's crust and mantle. Could these currents have played a role? It sounds like science fiction, but the connection between electromagnetism and seismic activity, known as seismoelectromagnetics, is a small but growing field of research. Some studies suggest that strong electrical currents flowing through certain types of rock can alter their frictional properties, potentially making it easier for a fault to slip. Could a comet-induced electromagnetic pulse have momentarily lubricated the critically stressed minerals deep within the Tonga subduction zone? Could it have provided the final nudge, not through pressure, but through a jolt of cosmic electricity? The team had no way to prove it, no model to test it. It was pure, unadulterated speculation, but it opened a door to a new way of thinking about our planet. It suggested that Earth is not an isolated system, that the boundaries between geology and astrophysics are more porous than we ever imagined. It hinted that we are connected to the cosmos not just by the grand, obvious force of gravity, but by subtle, invisible threads of pressure and electromagnetism. The skepticism within the group had not vanished, but it had transformed. It was no longer the dismissive certainty that the idea was wrong, but the cautious, rigorous skepticism of true scientists confronting a radical new paradigm. They had moved beyond the simple question of what if, and into the far more challenging territory of how could we know. The correlation was no longer just a curiosity, it had become a target for serious inquiry. The task ahead was immense. They would need to build complex atmospheric models, search for faint ionospheric disturbances in old satellite data, and scour the geologic record for other instances of deep earthquakes that coincided with the passage of celestial bodies. They would need to convince their peers to look at the data with fresh eyes, to suspend their disbelief long enough to consider that the most profound events on our world might just be triggered by the faintest whispers from another. The coincidence had become a hypothesis, and the hypothesis was now igniting a quiet, controversial, and utterly thrilling scientific revolution. And so the question hung in the air, a challenge so profound it threatened to fracture the very foundations of geology. A ghost from the Oort cloud, a fleeting visitor of ice and dust accused of reaching across 100 million kilometers of vacuum to strike a chord deep within our planet's iron heart. The initial response from the global scientific community had been predictably one of deep and profound skepticism. It was a theory that belonged more to the realm of fiction than to the rigorous, evidence-based world of geophysics. The energies involved were orders of magnitude apart a whisper, attempting to trigger an avalanche on a distant mountain. It was, by all conventional understanding, impossible. But science, in its purest form, is not about reinforcing what we know. It is about bravely, even recklessly investigating what we do not. And the earthquake, that impossible tremor from the forbidden zone, refused to be explained by conventional models. It was an anomaly, a dataset that screamed for a new perspective, and the strange temporal alignment with Comet 3I, Atlas, however improbable, was the only lead that remained on the table. Slowly at first, then with gathering momentum, the impossible idea began its transformation from a fringe hypothesis into a target for the most powerful analytical tools humanity could command. The moment of polite dismissal was over. The era of intense, organized scrutiny had begun. Across the globe, a silent, urgent mobilization was underway. It was a war waged on two fronts, one looking down into the hellish pressures and unimaginable heat of Earth's interior, the other looking up into the cold, silent precision of the cosmos. These two disciplines, seismology and orbital dynamics, which had for so long operated in separate universes of inquiry, were now being forced into an uneasy and unprecedented collaboration. At the vanguard of the downward-looking front were the seismologists, the interpreters of our planet's deep and often violent song. They were no longer merely listening to the earthquake's echo, they were preparing to conduct a digital séance. At supercomputing centers in Germany, Japan, and the United States, vast arrays of processors began to hum with a new purpose. These machines, capable of trillions of calculations per second, were tasked with building a virtual Earth, a digital twin of our world, rendered in breathtaking geophysical detail. They fed into it every scrap of data we have ever gathered, the precise composition of the crust, the plastic-like flow of the asthenosphere, the strange swirling dynamics of the liquid outer core, and the enigmatic solidity of the inner core, a sphere of iron hotter than the surface of the sun, yet crushed into a solid state. This was their stage, a perfect digital replica of our planet's soul. Then into this pristine model they introduced the ghost. They unleashed the seismic waves from the deep mantle event, not as a simple tremor, but as the unique high-fidelity recording captured by hundreds of sensors across the planet. They were trying to make the simulation scream in exactly the same way the real Earth had screamed. They watched as the virtual waves propagated outwards, refracting off the core mantle boundary, bouncing off the crust, interfering with one another in a dizzyingly complex dance. The goal was planetary forensics on an unimaginable scale, to reconstruct the scene of the crime, to understand the physics of the rupture itself. What kind of force could produce such a bizarre signature? The models at first failed spectacularly. A standard slip-fault earthquake, even one scaled to impossible energies, produced the wrong kinds of waves. It created shear waves that were too clean compression waves, that lacked the strange dissonant overtone that had so puzzled analysts. The real earthquake hadn't just been a simple rupture, a snapping of rock. The data suggested something more complex, almost musical. There was a faint but persistent harmonic resonance in the signal's tail, a secondary vibration that clung to the primary shockwave like a shadow. It was as if a bell had not only been struck but had been made to ring at a frequency it was never designed to produce. The teams worked relentlessly, tweaking the parameters of their models. They experimented with exotic geological mechanisms. Could a vast plume of superheated mantle material have suddenly collapsed? Could a fragment of the lower mantle, a slab of ancient subducted crust, have undergone a catastrophic phase change, its crystal structure instantaneously shifting under the immense pressure, releasing a burst of energy. Each hypothesis was modeled, simulated, and ultimately discarded. None of them could reproduce that strange spectral harmonic. The earthquake's unique voice remained a mystery, a cry from the abyss whose grammar they simply could not comprehend. The Earth was guarding its secret. Simultaneously, on the second front of this great investigation, astronomers and orbital dynamicists were looking upwards, undertaking a task of equally daunting precision. Their subject was the accused comet 3I, Atlas. They had to move beyond the simple, elegant Newtonian ellipses that govern the placid dance of planets. A comet is a far wilder beast. Its path through the solar system is a brawl between gravity and sunlight. As it neared the Sun 3I, Atlas had begun to disintegrate, venting jets of gas and dust from its heated nucleus. These jets were not uniform. They were chaotic, unpredictable eruptions that acted like tiny, erratic rocket thrusters, nudging the comet off its purely gravitational path. This phenomenon, known as non-gravitational forces, had to be meticulously calculated. Using every available telescopic image from its discovery to its demise, teams of specialists built a precise second-by-second timeline of the comet's journey. They mapped the locations and intensity of its outgassing jets, reconstructing its trajectory not just as a point of light, but as a dynamic, evolving object with its own chaotic agency. Their goal was to know exactly where the comet was and what it was doing at the precise moment of the deep earthquake. They refined its position in space relative to Earth, whittling down the uncertainties from thousands of kilometers to mere hundreds. It was the celestial equivalent of placing a suspect at the scene of the crime. Once the path was locked, the far more challenging work began: the search for a plausible physical interaction, a weapon that the comet could have used to influence the Earth. The most obvious force, gravity, was the first to be dismissed. Even at its closest approach, the comet's mass was insignificant. The gravitational tidal force it exerted on our planet was infinitesimal, less than the pull of a commercial airliner flying overhead. It could not by itself hope to fracture rock 30 times stronger than steel, nearly 700 kilometers beneath the surface. This was the great wall of impossibility the theory had to climb. If not gravity, then what? The investigators cast a wider net, venturing into the more exotic realms of physics. Could the comet's magnetic field, however weak, have somehow coupled with Earth's own powerful magnetosphere? They modeled the interaction, simulating the collision of these two invisible fields. The results were negligible. The comet's field was a tiny magnetic bubble, instantly overwhelmed and swept aside by Earth's powerful defenses, never coming close to touching the planet itself. They considered the comet's dust tail. Could a stream of fine particulate striking the upper atmosphere transfer enough kinetic energy downwards? Again, the calculations returned a resounding no. The mass of dust was too small, the energy dissipated harmlessly as microscopic meteors high above the ground. Every avenue seemed to lead to a dead end. The chasm between the two events, the dying comet and the shuddering Earth, seemed as unbridgeable as ever. The teams worked in parallel, separated by disciplines and distance. The seismologists staring at their stubbornly anomalous waveforms, the astronomers staring at their models of a beautiful but impotent comet. For weeks, the two fronts reported nothing but failure, and the mainstream scientific consensus began to settle back into its comfortable skepticism. The correlation, it seemed, was destined to be filed away as one of history's great unsolved coincidences. And then, from a small university in Italy, came the first whisper of a breakthrough. A team of plasma physicists, originally unassociated with the main effort, had taken a different approach. They were not interested in the comet's gravity or its dust. They were interested in its ghost, its plasma tail. This was not the familiar, gracefully curving dust tail visible to the naked eye. This was the second tail, a stream of ionized gas of atoms stripped of their electrons, pushed away from the comet not by sunlight, but by the solar wind. This tail is a river of charged particles, a filament of cosmic electricity stretching for millions of kilometers through space. And as 3I, Atlas, passed by Earth, this invisible ethereal appendage had washed directly over our planet's magnetosphere. The Italian team modeled this specific interaction with excruciating detail. They saw what others had seen, the plasma tail being deflected, parting around the Earth's magnetic shield like water around a boulder in a stream. But their model was more sensitive. It detected a secondary effect, a subtle low-energy resonance. As the charged particles of the tail interacted with the outer boundary of our magnetosphere, they generated waves not of light or of sound, but of magnetism. These were ultra-low frequency waves, oscillations in the magnetic field itself, with wavelengths thousands of kilometers long. They were incredibly faint, a magnetic hum almost lost in the background noise of space. Ordinarily, such waves would be harmless, carrying almost no energy. They would wash over the Earth and vanish. But the model showed something happening as 3I, Atlas, began to violently disintegrate. As the comet's nucleus fractured, the jets of gas became erratic, pulsating in a chaotic rhythm. This rhythm was imprinted onto the plasma tail, and in turn, it was imprinted onto the magnetic waves being generated at Earth's bow shock. For a few crucial hours during the comet's most violent death, throes the faint magnetic hum it was producing ceased to be random noise. It began to pulse, to oscillate at a very specific, very stable frequency, a frequency of just a few millihertz. A beat so slow you would have to listen for minutes to hear a single cycle. The dying comet, for a brief window in time, had become a cosmic tuning fork broadcasting a single, incredibly faint note across interplanetary space. By itself, this discovery was merely an interesting curiosity. A faint, slow pulse of magnetic energy from a dying comet was still a whisper trying to move a mountain. It was a weapon with no power. The breakthrough came when this information was shared almost as an afterthought with the seismology teams. A young postdoctoral researcher at Caltech, staring at the persistent, unexplained harmonic in the earthquake signal, felt a jolt of recognition. He isolated that strange secondary vibration, the signal's ghost, and measured its frequency. Then he ran the calculation to convert the magnetic frequency from the Italian team's data into a vibrational equivalent. The numbers were a perfect match. It was the critical piece of data, the key that suddenly impossibly threatened to unlock the entire puzzle. The faint harmonic overtone that had haunted the seismic recordings, the note the Earth was never supposed to be able to sing, was precisely the same note the dying comet had been humming. The revelation sent a shockwave through the investigation. Suddenly, they had a potential mechanism, a physical link that was not based on brute force, but on something far more subtle and far more potent: resonance. Resonance is the principle that allows a small periodic push to create a massive effect. It's how an opera singer can shatter a crystal glass with their voice alone. They don't overpower the glass. They find the precise frequency at which the glass naturally wants to vibrate, and they feed it energy at that exact rate, causing the vibrations to build and build until they overwhelm the structural integrity of the crystal. The new electrifying hypothesis was that 3I, Atlas, had not punched the Earth. It had sung to it. The supercomputer models were retasked with a frantic urgency. Now, armed with this new theory, they didn't just simulate the earthquake. They simulated the moments leading up to it. They built a model of the deep mantle not as a static solid rock, but as a region under immense near-breaking strain. Geologists have long known that the subducting tectonic plates that dive into the mantle can get stuck snagged on the boundary of the more viscous lower mantle, building up stress over millions of years. The region where the earthquake originated was known to be one such place, a geological snag point of unimaginable tension. It was a system primed, a structure already trembling on the verge of failure. Then into this virtual high-stress environment they introduced the comet's signal, not as a physical impact, but as a subtle, pervasive periodic vibration, a faint magnetic pulse tuned to that one specific resonant frequency. And they watched. For hours of simulation time, nothing happened. The faint energy was absorbed and dissipated by the vastness of the mantle. But the model kept running, and the gentle, persistent pushing continued. The vibration carried by the magnetic field penetrated the planet, reaching the stressed rock of the core mantle boundary. And there, deep in the digital Earth, something began to stir. The rock, already under 1,000 gigapascals of pressure, began to resonate with the cometary signal. The vibration, though infinitesimally weak, was a perfect match for the natural resonant frequency of the stressed mineral lattice. Atom by atom, the oscillations began to grow. The gentle rhythmic push was being amplified, focused by the unique geology of that one specific location. A tiny vibration amplified over hours by the power of resonance was adding the final infinitesimal grain of stress to a system that had been poised on a knife's edge for millennia. The researchers gathered around the monitor, watching in stunned silence as the energy levels in the simulated rock climbed slowly, then faster and faster. They were witnessing the scientific equivalent of a crystal glass beginning to tremble just before it shatters. The whisper from the comet was becoming a roar inside the Earth. Then the breaking point was reached. A microscopic fracture appeared, then instantly cascaded through the super-stressed rock in a chain reaction of catastrophic failure. The energy of 1,000,000 years of strain was released in a fraction of a second. The virtual Earth shuddered, unleashing a torrent of seismic waves. And when the team analyzed the signature of their simulated quake, they found it. There, clinging to the primary shockwave, was the unmistakable presence of the strange harmonic overtone. The ghost in the machine. The model was not definitive proof. A simulation, no matter how sophisticated, is only a representation of reality, not reality itself. But it was a stunning, compelling piece of evidence. It presented a physically plausible, if extraordinary, chain of events. It demonstrated that the comet's influence, while far too weak to directly cause the quake, could have acted as the trigger. It was the final straw, the tiny resonant tap that brought a mountain of stress crashing down. The idea, once dismissed as impossible fantasy, now had a theoretical framework, a tentative, contested but scientifically grounded explanation. The response from the wider community was electric and deeply divided. Many hailed it as a paradigm shift, a breathtaking discovery that connected the Earth and the cosmos in a way never before imagined. It opened up the terrifying and awe-inspiring possibility that our planet is not an isolated fortress, but a sensitive instrument capable of hearing the faintest whispers from the void. But for every convert, there was a skeptic. Veteran geophysicists remained wary, pointing out the long chain of improbabilities that had to align perfectly for the theory to work. They argued that an undiscovered, purely terrestrial mechanism was still a more likely, if less exciting, explanation. The gauntlet had been thrown down. A ghost had been found in the machine. But was it a true phantom from the depths of space, or merely a seductive reflection of their own desire to find one? To answer that, they would need more than a simulation. They would need to find a smoking gun, and so for a fleeting, breathtaking moment it seemed we had found it. A thread of influence stretching across the vacuum, a physical link between the fury of a dying comet and the deepest convulsions of our own world. The data points aligned with chilling precision. The timing appeared too perfect, too poetic to be mere chance. A message from the cosmos written not in light but in seismic energy, delivered from a disintegrating celestial wanderer. But in science, the most beautiful stories are often the most fragile. They are held up to the harshest lights, prodded and tested from every conceivable angle, because the universe is under no obligation to be poetic. And as the initial shockwave of the discovery subsided, a new wave began to build within the scientific community. Not one of excitement, but of profound, unyielding skepticism. The hypothesis, as elegant as it was about to collide with the brutal realities of physics. It was about to face its trial by fire. The first and most formidable wall of doubt was built of pure numbers, a question of energy of scale so vast it bordered on the absurd. Consider what we are truly proposing here. A piece of ice and rock, perhaps only a few kilometers across, shattering under the sun's glare, nearly 100 million miles away. And deep within our planet, a volume of rock the size of a city, violently shearing itself apart under pressures we can barely model. The 2021 Bonin earthquake released an almost unimaginable amount of energy, equivalent to the detonation of millions of tons of high explosive. This was not a subtle tremor. It was a planetary spasm originating in the crushing darkness of the lower mantle. The laws of physics demand a simple accounting. To influence an event, you must deliver sufficient energy to it. Where the critics asked was the energetic bridge. How could the distant death throw of Comet Atlas possibly deliver a knockout blow to a system already under such colossal strain? Think of the comet's influence as a whisper in a must of a Mar hurricane. The forces at play, 750 kilometers beneath our feet, are titanic. The immense lithospheric slab of the Pacific Plate, a continent-sized raft of rock, has been grinding its way down into the geological furnace of the mantle for millions of years. It descends under its own colossal weight, a slow-motion avalanche of unimaginable proportions. The pressures are over 25 gigapascals, a force so intense it can crush atoms into new crystalline forms. The temperature exceeds 1,000 degrees Celsius. This is a realm of alien physics where solid rock can flow like putty and where minerals are squeezed into configurations that cannot exist anywhere on the surface of the Earth. This is the earthquake's native environment. The energy for its rupture was already there, stored in the rock accumulated over millennia of relentless subduction. The question then is not whether the comet times caused times the quake, but whether it could have provided the final infinitesimal nudge. Could it have been the feather that tipped the scales, the proverbial straw that broke the camel's back? To answer that, we must examine the messengers of that influence. The most obvious candidate is gravity. Every object in the universe pulls on every other object. As the comet's fragments dispersed, their collective gravitational field would have shifted subtly, changing the pull on our planet. But the key word here is times, subtly, asterisk. Gravity is a force governed by the merciless inverse square law. Its influence drops off dramatically with distance. We live our entire lives bathed in the gravitational grip of celestial titans. The Moon, 250,000 miles away, is a gravitational powerhouse that heaves our oceans back and forth, creating tides that warp the solid crust of the planet itself. The Sun, though much farther, is so massive that its tidal force is still nearly half that of the Moon's. Day in and day out, these forces knead and stretch our world, yet we do not see a perfect correlation between tides and the triggering of the world's deepest earthquakes. Now compare that to Comet Atlas. At its closest, it was still hundreds of times farther away than the Moon, and its mass was a mere speck, an insignificant grain of sand compared to the heft of our lunar companion. Calculating the tidal stress exerted by the comet's fragmentation reveals a force so small it becomes almost a rounding error. It would be less than a billionth of the tidal forces our planet experiences from the Sun and Moon every single day. To suggest such a feeble gravitational whisper could find its way down through the crust, through the asthenosphere, through the entire upper mantle, and precisely trigger a fault already under millions of atmospheres of pressure, it stretches the bounds of physical plausibility to the breaking point. It asks us to believe that a butterfly flapping its wings in Brazil could not only cause a hurricane in Texas, but that it could choose the exact street the hurricane would strike. If gravity fails as a credible messenger, what else is there? The team behind the hypothesis knew they needed a more exotic mechanism, a way to focus the comet's energy into a planetary scalpel. One proposal invoked the powerful forces of electromagnetism. Comets are not merely passive chunks of ice. They are dynamic bodies interacting with the solar wind, a constant stream of charged particles flowing from the sunday. This interaction creates a vast ionized cloud of gas and dust, a plasma tail, and an encompassing magnetic field of its own. When 3I, Atlas, disintegrated, it wasn't a silent affair. It was an explosive release of gas and charged particles, a chaotic electromagnetic event. Could a pulse, a shockwave of this plasma have washed over the Earth and somehow penetrated its defenses? It's an intriguing idea, but it runs headlong into Earth's own formidable shield, the magnetosphere. This magnetic bubble generated by the churning liquid iron in our planet's core is our first and best line of defense against cosmic radiation. It deflects the solar wind and traps charged particles in the Van Allen belts miles above the surface. Any plasma cloud from the comet would have first encountered this shield. The resulting collision would have been spectacular, yes. It might have generated brilliant auroras, shimmering curtains of light dancing in the polar skies. It might have caused minor disturbances in radio communications or satellite orbits, but the notion that this interaction could transmit a coherent, powerful energy signal deep into the mantle is profoundly difficult to support. The energy would be absorbed, deflected, and dissipated in the upper atmosphere, a celestial buffer zone. The atmosphere itself, a 100-kilometer thick blanket of gas, provides yet another layer of insulation. By the time any remnant of that energy reached the ground, it would be a ghost of its former self, incapable of influencing anything beyond the most sensitive instruments, let alone the titanic mechanics of a subducting plate. It's like trying to feel the heat of a distant campfire through a castle wall. The raw physics of attenuation and shielding makes the connection seem less like a scientific theory and more like a work of fiction. Proponents searching for a particle that could make the journey were forced to consider the strangest, most elusive messenger of all, the neutrino. These ghost particles are born in the hearts of stars and in violent cosmic events. They have almost no mass and no electric charge, allowing them to pass through ordinary matter as if it weren't there. Billions of neutrinos from our own sun are streaming through your body, through the entire planet, every single second, and we feel absolutely nothing. Their interaction with matter is extraordinarily weak. Could the comet's breakup have produced a focused beam of these particles, a unique high-energy burst that against all odds deposited its energy at just the right point in the mantle? This idea enters a realm of pure speculation, requiring new physics, new models of cometary disintegration that have never been observed or theorized. Even if such a burst were produced, the probability of even one of those neutrinos interacting with a single atom in the target zone is infinitesimally small. To have enough of them interact to transfer the kind of energy needed to trigger a deep earthquake would require a beam of such intensity that the comet itself would have to have been a phenomenon unlike anything ever witnessed in human history. There is simply no evidence for such a thing. The neutrino hypothesis, while imaginative, was seen by most of the community as a bridge too far, a desperate attempt to connect two dots with no discernible line between them. Without a plausible physical mechanism, a way to get the signal from point A to point B, the entire theory teeters on the brink of collapse. This leads to the most powerful, the most elegant, and for some the most unsatisfying counterargument of all. It requires no new physics, no exotic forces, no speculative mechanisms. It requires only an acceptance of the laws of probability. The argument is simply this: it was a coincidence. A staggering, beautiful, mind-bending coincidence, but a coincidence nonetheless. Our brains are wired to find patterns, to seek cause and effect. We see a comet shatter, we see the Earth shake, and we instinctively draw a line between the two events. But the universe is a vast and busy place filled with an almost infinite number of overlapping events. On any given day, comets are brightening and fading. Asteroids are tumbling through space. Stars are exploding in distant galaxies. And simultaneously here on Earth, our planet is constantly in motion. There are, on average, several earthquakes every single minute. While quakes as deep and powerful as the Bonin event are much rarer, they are not unique. The region where it occurred, the Izu-Bonin Trench, is one of the most geologically violent places on the planet. Deep quakes are an expected if infrequent feature of its behavior. So was it really so improbable that one such quake would happen to occur within the same window of time that a small distant comet was breaking apart? Statisticians will tell you that with a large enough sample size, even the most improbable events become inevitable. If you flip a coin enough times, you will eventually get 20 heads in a row. If you deal enough hands of cards, someone somewhere will eventually be dealt a royal flush. In a cosmos that has been running for 13.8 billion years, and on a planet that has been geologically active for more than 4 billion, the number of chances for a celestial event to align with a terrestrial one is astronomical. The 3I, Atlas hypothesis, hangs entirely on the razor's edge of timing. But without a physical causal link, timing alone is just a story we tell ourselves. It is an anecdote, not data. The scientific community, by its very nature, is wary of anecdotes. It demands a repeatable, testable physical explanation. The coincidence argument offers just that the event was triggered by the same internal processes that have been triggering deep earthquakes for eons. The comet was merely a silent, indifferent spectator, its own drama playing out on a completely separate cosmic stage. It's a less exciting explanation. It robs the story of its magic. but it has the distinct and powerful advantage of requiring nothing more than the known laws of nature, and it forces us to remember what we times do times know about these abyssal tremors. The science of deep earthquakes, while still incomplete, is not a total mystery. We don't need a cosmic trigger to explain them because we have powerful candidates right here at home. The leading theory centers on a phenomenon called phase transformation. As the cold, subducting slab of oceanic crust plunges deeper, it encounters ever-increasing pressure and temperature. Minerals within the slab that were stable at the surface, like olivine, suddenly find themselves in a profoundly hostile environment. They become metastable like a house of cards waiting for a breath of wind. At a critical depth around 660 kilometers, the pressure becomes too great. The olivine atoms spontaneously rearrange themselves into a denser, more stable crystal structure called ringwoodite. This transformation happens with blistering speed, and critically it causes the volume of the rock to shrink. If this process happens rapidly enough across a large enough area, a phenomenon known as transformational faulting, it can create a shear instability, a sudden slip that releases hundreds of years of accumulated stress in a matter of seconds. The rock doesn't break like a brittle plate on the surface. It fails on a crystalline level. It's a mineralogical time bomb. Its fuse lit the moment the slab began its descent. This model and others like it, involving thermal runaway and dehydration embrittlement, provide a complete self-contained explanation for deep earthquakes. They are a natural, albeit terrifying, consequence of plate tectonics. They are the groans of a living, breathing planet. To the geophysicists who have spent their careers modeling these processes, the introduction of a comet feels like an unnecessary complication, a solution in search of a problem. Why look to the heavens for a trigger, they argue, when the engine of destruction is already churning away right under our feet? This is the gauntlet thrown down. This is the crucible in which every revolutionary idea is tested. The scientific method is a stern gatekeeper. It demands evidence that is not just compelling but overwhelming. Extraordinary claims require extraordinary proof. And the claim that a distant comet reached across the void to trigger one of Earth's deepest secrets is among the most extraordinary of all. For the community to accept it, the proponents must do more than point to a coincidence in timing. They must build that energetic bridge stone by stone. They must present a physical model, one that can be tested, simulated on a supercomputer, and make predictions about future events. They must show with undeniable mathematics how the whisper from Atlas could be heard over the roar of the mantle. Without that bridge, the connection remains a ghost, a tantalizing speculation, a story written in the language of chance, haunting the edges of our understanding. The burden of proof is absolute. And as the debate raged on, the team behind the initial discovery knew that they had to find something more, some new piece of evidence that could silence the critics and turn their beautiful, fragile story into accepted scientific fact. They had to return to the data, to the signals from deep inside the Earth, and listen again for the echo of a distant dying comet. And so here we are, suspended between two immensities. On one side, the ghost of an interstellar wanderer, a fleeting courier from a star system we will never know now, scattered into a stream of cosmic dust and ice. On the other, a tremor from the very bowels of our own planet, a convulsion of rock so deep it challenges the known physics of our world. We have laid the pieces on the board, the impossible timing, the unnerving geographic alignment, the sheer alien nature of both events. Now the time for speculation recedes, and the hard, cold process of judgment must begin. The central question of our entire journey can no longer be deferred. We must weigh the evidence, confront the paradoxes, and ask with unforgiving clarity, did a fragment of 3I, Atlas, a messenger from beyond our sun's embrace, truly reach out and trigger the deepest earthquake ever recorded? Could such a bug thing even be possible? Let us first, as any fair tribunal must, entertain the prosecution. We must give voice to the audacious hypothesis that connects the heavens to the underworld. The argument begins with a coincidence so profound it feels like a conspiracy of physics. For a brief critical window in May of 2015, Earth's orbital path intersected the debris trail left by the disintegrating comet, Models refined with every new observation show our planet ploughing through this tenuous river of interstellar material. And at the precise moment of this crossing, 751 kilometers beneath the waves of the Pacific, a locked section of the Earth's crust, a place of unimaginable pressure, violently slipped. The temporal link is not merely suggestive, it is almost perfect, a synchronized dance between a celestial event and a terrestrial cataclysm. To dismiss this as mere chance requires a comfortable faith in probability, a faith that crumbles slightly when we consider the location. The epicenter of the Izu-Ogasawara quake was not just anywhere on the planet. It was located almost directly beneath the predicted atmospheric entry point for the densest part of the comet's debris stream. The geometry is haunting. Imagine a cosmic sniper firing a projectile from the outer solar system. The bullet, traveling for millennia, arrives at the exact instant the target passes, striking it in the precise spot required to provoke a reaction. The alignment in time and space is the cornerstone of this entire investigation, a foundation of circumstantial evidence so strong it practically begs for a physical explanation. What could that explanation be? We are not talking about a planet-killer asteroid, an impact that would boil oceans and crack continents. The theory demands a far more subtle, almost surgical mechanism. Proponents envision a unique projectile. Not just a piece of dirty ice, but a dense core fragment of 3I, Atlas, forged in the heart of another solar system with a composition unlike our own. Perhaps it contained a higher concentration of heavy elements like osmium or iridium, making it a kind of cosmic cannonball. This object, maybe no larger than a small car, would not have announced its arrival with a brilliant fireball. Its immense velocity, a product of its interstellar trajectory, would have allowed it to punch through the atmosphere with minimal ablation striking the ocean's surface, not with a concussive blast, but with the focused, penetrating energy of a hypervelocity round. It would have vaporized a column of water in an instant, transferring its staggering kinetic energy into the sea as a focused pressure wave, a hydraulic hammer strike aimed directly at the seabed below. Could this shockwave, this precisely aimed pulse of energy, travel through miles of water and kilometers of crust, arriving at the subducting Pacific plate with just enough force to be the final straw? Could it be the feather that breaks the camel's back, nudging a critically stressed fault line over the precipice into catastrophic failure? There is another, even more exotic possibility whispered among the theory's adherents. What if the trigger wasn't mechanical at all? Comets are not inert rocks. They are dynamic bodies crackling with electromagnetic potential, interacting with the solar wind to create complex magnetospheres. An interstellar comet, having traveled through the vastly different magnetic environments between stars, might possess unique electrical properties. If a fragment of 3I, Atlas, was unusually rich in conductive materials, its hypervelocity passage through Earth's own magnetic field and atmosphere could have generated an immense electromagnetic pulse, or EMP. This pulse, a phantom burst of energy, would leave no crater, no visible trace, but it could have induced powerful electrical currents deep within the Earth's crust, in the mineralogically complex and water-rich environment of the subduction zone. Such telluric currents are known to occur naturally, but an externally generated pulse of this magnitude would be unprecedented. Could this invisible jolt of electricity have been the catalyst altering the frictional properties of the rock, or triggering a phase change in minerals like olivine, a transformation we know is linked to these ultra-deep quakes? It is a mechanism bordering on science fiction, yet it elegantly explains the most troubling part of the mystery, the complete and total lack of a smoking gun. There is no crater, no observed bolide, no recovered meteorite. There is only the quake itself, a seismic ghost screaming from the abyss at the exact moment a celestial phantom passed overhead. This is the case for the impossible, a chain of perfect timing, perfect location, and speculative but tantalizing physics. A narrative so compelling, so poetically grand, that we desperately want it to be true. But now the defense must have its turn, and it comes armed not with poetic narrative but with the cold, brutal mathematics of geophysics. The first and most devastating argument against the connection is one of simple energy. The scale of the forces involved in a deep focus earthquake is difficult for the human mind to comprehend. 751 kilometers down, the pressure is over 25 gigapascals. That is like having the weight of 50,000 jumbo jets balanced on the tip of your finger. The rock there is not brittle. It is a superheated plastic flowing like celestial taffy over geological time. The energy released by the Izu Ogasawara earthquake was equivalent to the detonation of over 30 thermonuclear bombs. It was the planet itself in a moment of profound internal adjustment, unleashing a force that dwarfs human experience. Now consider the proposed trigger, a cometary fragment. Even being generous, assuming a dense car-sized object traveling at interstellar speeds, the kinetic energy it carries upon impact is enormous, certainly enough to level a city. But compared to the stored tectonic strain in that subducting plate, it is a whisper in a hurricane. It is a single raindrop landing on the deck of a battleship already being torn apart by a typhoon. The energy budget simply does not balance. For a pressure wave from the surface to retain enough power to influence events at that staggering depth, it would need to be so powerful at its source that the impact itself would have been a globally catastrophic event, one that would have left no doubt as to its occurrence. There would have been a tsunami of biblical proportions, an atmospheric shockwave detected on every barometer on Earth. There was nothing, just silence. This silence is the second great pillar of the counterargument. Our planet is wired for sound. A global network of infrasound sensors, originally designed to detect clandestine nuclear tests, listens constantly for the low-frequency rumble of large explosions. A hypervelocity impact of the kind required by the theory would have generated a monumental atmospheric pressure wave, a booming signature that would be utterly unmistakable. The network heard nothing. Our skies are watched by military and civilian satellites, a celestial neighborhood watch programmed to spot the infrared flash of missile launches and re-entering space debris. An object punching through the atmosphere at such speeds would have created a thermal signature brighter than any meteor. The satellites saw nothing. Our oceans are monitored by hydroacoustic sensors, a web of underwater ears that can detect the sounds of submarines from thousands of miles away. The impact of a multi-ton object and the subsequent vaporization of a massive column of water would have screamed through the ocean's deep sound channel. The hydrophones heard nothing, and most damningly of all, the world's seismometers, the very instruments that detected the earthquake itself, registered no preceding impact event. An oceanic impact creates a specific seismic signature, a P-wave signal that is completely different from the onset of a tectonic quake. That signature is absent from the record. In the court of science, an absence of evidence when evidence is expected is indeed evidence of absence. The trigger, if it existed, was a ghost that passed through every single one of our planetary defense systems without leaving a single footprint. And so we are brought to the spectre of coincidence. Our brains are pattern-matching machines. We see faces in the clouds and constellations in the stars. The scientific term is apophenia, the tendency to perceive meaningful connections between unrelated things. Every single day, the Earth is struck by dozens of tons of extraterrestrial material. Every single day, there are thousands of earthquakes rumbling across the globe. With so many events occurring constantly, both above us and below us, finding two dramatic ones that happen to align in time and space is not just possible, it is over a long enough timescale, statistically inevitable. The Izu Ogasawara earthquake was a one-in-a-generation event. The passage of a naked-eye interstellar comet is a once-in-a-lifetime event. Was their temporal proximity a sign of a profound cosmic link? Or was it simply the universe rolling the dice and coming up with 2 sevens in a row? This is the frustrating, unsatisfying, but intellectually honest core of the skeptical position. Without a physical mechanism that can survive the brutal scrutiny of energy calculations, and without a single shred of direct corroborating physical evidence, the connection remains a captivating story, a piece of cosmic folklore, but not a scientific conclusion. The principle of Occam's razor that the simplest explanation is most likely the correct one hangs over the entire affair, and the simplest explanation is that a highly unusual but entirely terrestrial earthquake occurred. It was an internal affair, a drama played out exclusively within the Earth's mantle. The strange rupture, the immense depth, these are puzzles for geophysicists, pushing them to refine their models of plate tectonics and mineral physics. They are not, the consensus argues, clues to an extraterrestrial intervention. The earthquake can be explained, however, imperfectly, using the forces and materials we know exist within our planet. Invoking an invisible, undetectable, and energetically insufficient comet fragment is an extraordinary claim that requires extraordinary evidence. And that evidence quite simply does not exist. So where does this leave us? We have followed the trail to its end. We have weighed the tantalizing coincidences against the unyielding laws of physics. We have pitted a beautiful narrative against a mountain of missing evidence. The verdict of the scientific community arrived at, not with triumphant fanfare, but with a quiet, considered certainty, is now clear. The connection between 3I, Atlas, and the Izu Ogasawara earthquake is deemed to be a phantom. The causal link is almost certainly an illusion, a magnificent but misleading juxtaposition of two unrelated, awe-inspiring events. The data, when analyzed without the bias of a desired narrative, points overwhelmingly to coincidence. It is a conclusion that may feel disappointing, a grand cosmic mystery that resolves into a mundane statistical anomaly. It feels like a story with the final climactic chapter torn out, but perhaps that is the wrong way to look at it. The real value of this investigation was never contingent on the answer being yes. The true victory lies in the audacity of the question itself. By daring to propose such a wild connection by chasing this celestial ghost, scientists were forced to push their understanding to the absolute limit. Seismologists had to re-examine their models of deep Earth mechanics, questioning the very triggers that can operate under such extreme conditions. Astronomers were compelled to refine their calculations of cometary debris trails, improving their ability to predict how these ghostly streams interact with our planet. The investigation forced two disparate fields of science, the study of the deepest Earth and the study of the farthest visitor, to speak to one another, to share data, to challenge each other's assumptions. The result is a richer, more nuanced understanding of our world and its place in the cosmos. We learned that even an impossible hypothesis can be a powerful tool, a catalyst for discovery that illuminates the dark corners of our knowledge. We have proven the link to be a phantom, but in chasing that phantom we have mapped the haunted house in unprecedented detail. The case for 3I, Atlas as the trigger then, is closed. The documentary's central question has its answer, and that answer is a firm data-driven no. But the larger mysteries that this journey has unearthed are only just beginning to open. The Izu Ogasawara earthquake remains a profound enigma. If a cosmic impact was not the cause of its bizarre and complex rupture, then what was? What unknown process is at work in the planet's hidden depths, capable of unleashing such fury from a place we thought was quiet? And what of 3I, Atlas itself? It was only the second interstellar object ever detected passing through our solar system. Its arrival was a reminder that our sun's neighborhood is not an isolated island, but a busy thoroughfare, constantly visited by messengers from other stars. We now know with absolute certainty that we are not alone in this way. The galaxy is sending us packages, samples from distant unknown worlds. Most pass by unnoticed. But what about the next one, and the one after that? The story of 3I, Atlas, may be over, but the era of interstellar visitors has just begun, and we are left with a new, more unsettling question. What else is out there already on its way? And so, after this long and winding journey through the cosmos and into the very heart of our own world, we are left here standing at the edge of certainty. We have chased a ghost through the solar system, a phantom whisper that travelled from the silent, frozen depths between the stars, through the fury of our sun, to perhaps, just perhaps, deliver a final resonant blow to the deepest sanctum of our planet. The link between the interstellar comet 3I, Atlas, and the profound world-shaking tremor that originated from a place we once thought was geologically silent remains a tantalizing, maddeningly ephemeral thread. We have followed the chain of evidence, a sequence of extraordinary possibilities, each link forged in the fires of rigorous scientific debate. We saw the comet's strange premature disintegration, a sudden and violent end to a journey that lasted millions of years. We tracked its debris stream, a river of ice and dust, and plotted its intersection with Earth's orbit, a cosmic crossroad where two travelers met by chance in the vast emptiness. We then plunged into the theoretical abyss, exploring how the most elusive particles in existence, of neutrinos, born from this cometary decay, could have acted as an invisible key, unlocking immense pent-up stress within Earth's lower mantle. Yet for every compelling piece of circumstantial evidence, for every computer model that screams possible, the cosmos withholds its final unambiguous confession. There is no definitive fingerprint, no single data point that transforms this incredible hypothesis into indisputable fact. The universe, it seems, is not yet ready to give up all its secrets. And perhaps that is the most important discovery of all. The true legacy of this investigation may not be found in a simple yes or no answer. Its profound importance lies not in the destination we hope to reach, but in the uncharted territory we were forced to map along the way. Whether Comet 3I, Atlas, ultimately proves to be the culprit, or merely a spectacular cosmic coincidence, the very act of asking the question has irrevocably changed our perception of the Earth and its place in the universe. We have been shaken from a long-held scientific slumber, a comfortable paradigm that viewed our planet as a fortress, a geologically self-contained sphere immune to the subtle whims of the cosmos. For centuries, we understood the external threats, the brutal kinetic impact of an asteroid, the searing blast of a nearby supernova. These were the hammers of the universe, loud, obvious, and devastating. But the story of 3I, Atlas, suggested a different kind of connection, something far more intimate and insidious. It proposed that Earth is not a fortress at all, but a finely tuned resonant instrument, a planetary tuning fork that can be struck by forces we are only now beginning to comprehend. It suggests that our world is in a constant, delicate dialogue with the wider cosmos, and that a whisper from a passing stranger millions of miles away could be enough to awaken a sleeping giant within our own core. This radical idea has forced a revolution, a shotgun wedding between scientific disciplines that had for generations resided in separate, well-ordered worlds. Before this investigation, the seismologist listening to the slow breathing of the planet's crust had little reason to speak with the astrophysicist whose gaze was fixed upon the dying light of distant galaxies. The particle physicist hunting for ghostly neutrinos in subterranean laboratories worked in a reality far removed from the geologist who reads the story of time in layers of rock. 3I, Atlas, and the deep quake that followed became a Rosetta Stone, a common language that forced these disparate fields not just to talk, but to collaborate in a way that was previously unimaginable. Suddenly, the complex decay patterns of an interstellar comet's nucleus became critically important to understanding tectonic stress release. The arcane physics of sterile neutrinos, once the domain of pure theoretical cosmology, was now being invoked to explain a geological event. We witnessed the birth of a new hybrid science, a synthesis of the incredibly large and the infinitesimally small. Geophysics was no longer just about the Earth. It had to become astrogeophysics. Seismology had to account for the particle stream of the solar wind, the flux of cosmic rays, and the gravitational ripples from passing objects. This investigation has shattered the artificial walls between disciplines, reminding us that in nature there are no such divisions. There is only a single, seamless, interconnected reality, a complex symphony of forces where the flapping of a butterfly's wings and the explosion of a distant star are all in some small but meaningful way part of the same cosmic composition. The true triumph isn't proving a single hypothesis, but in building these new bridges of understanding. The conversation started in the wake of this event will not end. They will echo in university halls, in research labs, and at mission control centers for decades, spawning new theories, new experiments, and a new generation of scientists who see the universe not as a collection of separate subjects, but as a single magnificent interwoven puzzle. And to solve that puzzle, we need better eyes and better ears. This entire saga has thrown a glaring spotlight on the limitations of our current technology, while simultaneously fueling the drive to overcome them. We are now entering a golden age of planetary and cosmic surveillance, an era where the what-if of 3I, Atlas, becomes a concrete observational target. Here on Earth, the quest to understand our planet's deepest secrets is accelerating. We are developing networks of deep Earth seismometers of unprecedented sensitivity instruments capable of not just detecting these profound quakes, but of mapping the mantle's structure with the fidelity of a medical ultrasound. Imagine deploying thousands of these sensors across the ocean floor in the deepest trenches, creating a global real-time nervous system for the planet. This would allow us to listen to the faintest murmurs of the lower mantle, to track stress as it accumulates and migrates over decades, potentially giving us the ability to forecast these deep, powerful events. Furthermore, neutrino observatories like IceCube in Antarctica are being reimagined. Once designed solely to look outward for cosmic sources, they are now being calibrated to use the Earth itself as a target, searching for anomalous interactions in the core and mantle. They could become our planetary scanners using ghostly particles from the Sun and beyond to probe the parts of our world that are forever hidden from direct observation. We could, in essence, perform a constant CAT scan of the entire globe, watching the subtle dance of matter and energy in its most secret places. Simultaneously, our watch over the heavens is being transformed. For every 3-eye atlas we catch, we know there are thousands we miss. These interstellar nomads are faint, fast-moving and unpredictable, gate-crashing our solar system with little warning. But observatories like the Vera C. Rubin Observatory in Chile are about to change the game entirely. When it comes online, this magnificent instrument will survey the entire visible sky every few nights, a relentless, wide-eyed stare into the cosmic darkness. Its sheer volume of data will be staggering, a digital torrent of information so vast that human eyes could never process it all. Instead, sophisticated artificial intelligence will become our celestial gatekeeper, sifting through billions of points of light to find the faint streak of an interstellar visitor. These AI systems will be trained to recognize the telltale signatures of these objects, flagging them for immediate follow-up by other telescopes around the world. We will move from a reactive mode, scrambling to study these comets and asteroids after they are discovered, to a proactive one, building a comprehensive catalogue of everything that crosses our path. We will be able to track their trajectories with incredible precision from much farther out, analysing their chemical composition and predicting their behaviour long before they reach the inner solar system. We will no longer be surprised by visitors like 3-Eye Atlas. We will be waiting for them. This global, interconnected network of terrestrial and celestial observatories represents the next great leap in our planetary defence and our cosmic awareness. It is the lasting, tangible legacy of a mystery that pushed us to the very brink of our knowledge, a tool forged in the crucible of a question that we dared to ask. In the end, our journey concludes where it began, with a sense of profound wonder. We look up at the night sky and it is no longer the same. It is not a serene, painted backdrop to our terrestrial lives, but a dynamic, interactive environment filled with invisible currents and subtle influences that can reach down and touch the very heart of our world. The silence we once perceived is now filled with the potential for connection, a constant unheard dialogue between our planet and the cosmos. The question, did 3-Eye Atlas trigger the deepest earthquake ever recorded, has served as a powerful catalyst. Even if future evidence ultimately refutes the link, the pursuit of an answer has been more valuable than the answer itself. It has forced us to confront our assumptions, to forge new alliances between different fields of science, and to build the tools that will unlock the next generation of discoveries. Scientific progress is not a straight line of proven facts. It is a messy, beautiful, creative process driven by curiosity, imagination, and the courage to ask outlandish questions. It is in chasing these wild ideas, these tantalizing possibilities that dance at the edge of reason, that we often make our greatest leaps. This investigation has reminded us that we are not merely residents on planet Earth. We are passengers traveling together on a living, breathing, geologically active spaceship, flying through a cosmic ocean that is far more complex and interconnected than we ever dreamed. Every atom in our bodies was forged in the heart of a star that died long ago. We are, in the most literal sense, creatures of the cosmos, and the story of a fragile comet and a deep earthquake is a powerful, humbling reminder that the boundary between our world and the universe is and has always been an illusion. The connection is real. We just have to learn how to listen.